Yes, and I have a very special topic selected for Thursday, so I strongly recommend you all be here. Um, and we'll have fun.
Are you a homework quiz on Thursday?
Of course you're going to have a homework quiz on Thursday. Your homework's due on Thursday. What kind of silliness is that, Ross? Yeah, you have a homework quiz on Thursday, but then we'll do something fun. We'll cover...
the homework quiz beer?
I have no control over you all and what you do. Oh man, I'm getting the texts at the messages at the bottom. Okay, let's get started, please. Yeah. Okay, so I hope to God I'm awake. I just finished up my chemo Saturday and I was super fatigued, so fatigued I couldn't meet with any of my research students last night, but I actually am feeling better today. So hopefully I can get through this lecture without going to sleep. If I do go to sleep, you guys keep the microphones muted so that you don't wake me up. Because it's chemo fatigue. It's pretty tiring and I just really need to sleep. Nice haircut, by the way, Madison. Anyway, all right. Oh, damn. Look who is on the first card. Whoops. It's...
Who was that? It was someone else. It was someone else.
Yeah, no, it's you, Madison.
Has spoken.
Okay, all right. So there's one quick thing I want to write down that I forgot to write down last time, and I'll actually pose it as a question. Madison, because you're on top. Last time when we were dealing with the Feynman rules for QCD, we encountered this thing which I just wrote as a matrix lambda alpha, and I said secretly I could give this indices, and then this is a matrix which links the gluon space, which has 8 gluons, to the color space. So I and J take values red, blue, green. So these take 3 values each, whereas this takes 8 values. But I didn't actually call that lambda what it was. Do you have any idea what that lambda actually is?
Do you mean like a tensor? Or like what is it?
Like what role does it play? I mean, sure, it's a matrix which happens to link up the gluon space to the color space, but what other role does that lambda play?
I'm not sure.
I actually mentioned it very early in that lecture, but I just kind of wrote it when I was writing the covariant derivative.
Isn't that the generator?
Yeah, it's the generator of SU3. So what I should have written was that lambda alpha, lambda beta, if I take the commutator of those, then I get an expression that looks like this: 2I F alpha beta gamma lambda gamma. Okay, and this is the Lie algebra which governs SU3, which is the underlying group of the strong interactions in the standard model. So I just wanted to point that out to you because I forgot to write that last time. But this is going to be important. So by the way, the lambdas here, you were introduced to in homework 2. So you might or might not remember, but long ago in a land far, far away, in homework 2, I gave you 8 matrices, and that corresponded to the generators of SU3, and you worked a little bit with the Lie algebra, and you did a few things with it. Well, we're going to use those today to evaluate some color factors. So, moving right along, we're going to explore at least 2 answers to 2 interesting questions, and they're not going to be super hyper concrete answers, but there's a reason why you can't get those answers in QCD, which I'll cover a little later on. So first, the first thing we're going to do is we're going to answer the question, why do we only find colorless bound states or color singlet bound states of quarks? Okay, now you might have remembered in various points of review, I said that, you know, one of the interesting things about quarks is that you can't have a single quark out there. You always have to have your quarks either come in pairs, where it's a quark-antiquark pair, and that's called a what, Andy? Andy is...
Andy doesn't come to this class anymore, so you should probably just get rid of his card.
All right. What about Andrew?
Hi,
Yeah.
I don't know for sure. Hold on one second. I'm looking through my notes.
That's okay.
Is that a meson?
Yeah, it's a meson, exactly. You found that pretty quickly. I'm impressed. Okay. Or you can have a bound state of 3 quarks or 3 antiquarks, and in that case, we call that a what? Same
Are you
page.
still,
Say it again?
what? Are you still asking me?
Yeah. Because it should be on that same page. A baryon, exactly. Okay, so we're going to investigate why quarks only exist as mesons, quark-antiquark pairs, or baryons. 3 quark or three antiquark pairs. And then the second question, if QCD is so strong, why is it swamped by QED at large distances? Okay? And, you know, hopefully you kind of realize this, you know, obviously QCD, which is the interaction between quarks, and therefore it realizes itself as the interaction between protons and neutrons, the nuclear interactions. We often think of the nuclear interactions as very strong, right? You know, nuclear bombs, or breaking apart a nuclear atom and releasing all that wonderful energy that's stored in the nuclear interaction. However, you know, if I'm sitting here holding this marker, nuclear interactions don't have a lot to do with it. It's all electromagnetic. Okay? So why the hell don't nuclear interactions play a role at large distances? Why is everything always governed by either gravity or electromagnetism in the standard model? So we'll investigate answers to both of these questions today. And let's get started with the first one. And this will take us somewhere which is eventually quite interesting. We've got a little bit of work to get through in order to get there. Okay, so I'm going to start by considering mesons, and then we'll turn to baryons, even though the baryon situation is way harder to analyze. So the idea is basically as follows. For mesons, if we think about assigning the colors to a meson, so a meson is a quark and an antiquark, and right now it doesn't matter what kind of quarks they are. It could be an up and an anti-up, an up and an anti-down. All that matters is that it's a quark and an antiquark, and therefore we have to assign one of 3 colors and one of 3 anticolors, but we don't necessarily have to do it in just the pairings, and you'll understand what I'm talking about in just a minute. Okay, so what we're going to discover is that for a colorless singlet combination, that is, if we take 2 quarks and we put them, or we assign the colors to them such that they are a colorless singlet, and I'll remind you what that means. I actually defined it last time, but I'll remind you what it means. Then what we discover is that the interaction between those 2 quarks is attractive. Okay? However, if we put the 2 quarks in any of the colorful octet states, then it turns out that the QCD force between the two quarks is actually repulsive. Now this is going to be an easy one. Is Dylan here? Dylan, you're here, yeah. Dylan. Which of these two cases do you think is most likely to describe things which form bound states?
Attractive.
Yeah, it's attractive. Okay? So it's hard to imagine two quarks which, you know, move along in this combination if they're experiencing a repulsive interaction between the two of them. Okay? So we're going to demonstrate that the colorless singlet combination is attractive and the colorful octet situation is repulsive. So here we go. At leading order, we can consider the following interaction. Where I'm just going to have a down quark, or I'll have an anti-quark and a quark. Okay, and I mean I might call this an up quark and a down quark just to give them names, but I could use any any anti-quark and quark state. And what we're of course considering here is just up. Anti-up, down, plus, or goes to, geez, Louise. Goes to, man, something is not working in me today. This is kind of scary. Okay, there we go. All right, so actually just to mimic my notes so I don't get myself screwed up, let me make this the down and this the up. And then I move the bars. Okay, so let me go ahead and label this real quickly. And these are momentum labels. I'm just giving them numericals. And then we might have the Q for the gluon, which we have going up. Okay, now, I laid out the Feynman rules for QCD for you last time. So right now I'm just going to write down the expression for M. Now remember, we're using pretty much everything that was a part of QED. So we make spinner sandwiches, and we've got vertex factors and propagators, internal propagators. And the only thing you have to do QCD is you have to add on a few things here and there, largely governing color and governing the generators. Okay? So I'm just going to go ahead and write down the expression for M, and then we're going to kind of bang it into something which we already know, and then something which is new. So the expression for M becomes the following. I U bar, I should have enough room. I U bar 3, C3, dagger, minus I GS over 2, lambda alpha gamma mu, U1, C1, now notice this is just the sandwich that we're obtaining by following the quark going in, and then the vertex operator, and then the quark coming out. Okay? And the only thing that's new over and above QED is the color factors for the external particles, and then this generator matrix. Otherwise, this looks just like a spinner sandwich from QED. Okay, now we have the propagator that describes this internal gluon. I'll go ahead and write that here. And I will try my best to write eta. No, I stupidly have it as G in my notes. And then we have another spinner sandwich, which is based on the outgoing anti-quark, the vertex, and then the incoming anti-quark. Okay, and this is actually m, so I'm not going to do the delta functions which conserve momentum at each vertex. Let's assume I've already done it. I've already done an integral over the momentum here. With the delta function, there's an overall delta function for the external momentum. I canceled that and I multiplied the thing by I, and this is what I got. Okay, we've done that enough that I hope I don't have to go through those steps again. All right, now, here is where this expression gets interesting. Sean, are you there? Sean?
Yes.
Oh yeah, you are. Good, good, good. Okay, so I got a question for you. This guy, is it a spinner or a vector or a humpback whale?
I don't think it's a humpback whale.
Good, good. I like the process of elimination. Spinner or vector?
I think it might be vector. Spinner?
Yes, yes, good. What, was it my smile?
It was.
Okay, good. That's awesome. Yeah, this is a spinner, okay? Is this trivial in spin space?
Is that a C?
Yeah, that's a C. That's a color factor.
Yes, so would that be a vector?
Well, no, no, no. It doesn't matter whether we call this a vector or not. It's trivial in spin space.
Okay, yes.
So this is trivial in spin space. This is a generator of the SU3. Is that trivial in spin space?
No, because it's a generator.
But it's not a generator of space-time transformations, which is where spin is important. It's a generator of SU3 color transformations. So do you think it's trivial in spin space?
No. Yes.
Yeah, good, good, good. That's awesome. Okay, so the moral to this story is that we can actually pull the color factors and the generators of SU3 out of these spinner sandwiches, and we don't have to worry about it. Okay?
Oh, nice.
What we do have to be careful about, and Sean, go ahead and mute yourself because I think we're getting feedback. What we do have to be careful about is that this is a dual color state. This is a matrix in color space, and this is a vector in color space. So we want to keep this order correct. Okay, so let me just pull out all those terms and show you what we got. Okay. So, yeah.
Sorry, what's the subscript on the G's? I just haven't been listening.
It's S. It's G strong.
Oh, gotcha. Okay.
Yeah, sorry, it's the strong coupling. Okay, so, all right. So what I want you to notice is that this thing right here all right, this whole quantity is exactly the m for E plus mu minus goes to E plus mu minus in QED with GS goes to GE. Okay? What I mean is this expression right here is exactly what we would have obtained if we had applied QED to the interaction of an electron, an anti-electron, and a muon. The only thing we'd have to change is this GS to GE. Okay? The only thing that's new and glorious in the QCD version of this calculation is this thing, which is built out of color sandwiches. There's two of them. Okay. I underlined the H in sandwiches. And this thing is overall called the color factor. All right? Now, the reason I'm doing this is as follows. This thing is exactly what we would have gotten if we had applied QED to the interaction of an anti-electron and a muon. Chance. I know you're there, Chance. Your video's not on, so it's hard to see your face, but Chance. Chance, is this an attractive or a repulsive electromagnetic interaction?
I'm going to say attractive.
Yeah, it's a positive and a negative charge. That's an attractive interaction. Okay? So, here is the observation I'm going to make. If the color sandwich here overall comes out to be a positive number, then this entire thing describes an attractive interaction. However, if the color sandwich comes out to be a negative number, then that implies that it's a repulsive interaction. And one of the ways to understand that is that the factor of m, which is what this thing represents, you can basically imagine is the evaluation of something like this if you're using effective potentials, okay? So you're transitioning from your initial state into your final state via the interaction with an external potential. And one of the things we know about whether an interaction is attractive or repulsive is it's the sign of the potential, okay? So the sign of M is really the thing that's going to tell us whether this interaction is attractive or repulsive. So all we have to do is evaluate the color factor. If it's positive, then it's attractive, and if it's negative, then it's repulsive. Okay? So let me clean this up a bit, and we'll do that explicitly. Okay. So here we go. Now, it's going to get a little tricky here. Instead of labeling the quarks, I'm actually going to label the colors that they're moving with. So I'm going to label this as a B, which since it's an anti-quark, then that's a B bar color, because anti-quarks only carry anti-color. And then we have a B bar come out, and then we're going to have a red come in and a red go out. Okay? So this is an octet state. Okay, now the overall state here is just RB bar. It's RB bar going in and RB bar going out. You might or might not remember, but in our last meeting, I gave you the octet states and the color singlet. And this octet is actually the linear combination 1 over root 2 of the first octet state plus I times the second of the 8 octet states that I gave you last time. But don't worry about it. Just remember those octet states, they were sums of a lot of things. So for example, state 1 was 1 over root 2 RB bar plus BR bar. Okay? And there are 8 of these linear combinations which form a basis in this color space. And the SU3 transformations just rotate these states into each other. Now this is opposed to the singlet, which is the state which is invariant under SU3, which we'll look at next. Okay? So, now, here's the cool part. This means that the color labels that we have to put on our external momenta are really simple. Because the label that we give for R as a 3-component vector is just 1, 0, 0. Okay? And that's, of course, the same vector that has to be on the outgoing quark. And then the label that we want to put for the B version of this is 0, 1, 0. And, of course, we have the same label for the outgoing one there. Okay? If I were doing a linear combination of colors, this would be more complicated, and I'll show you an example of that in a few minutes. But the only reason I'm doing this linear combination is because it gives me a pure R and a pure B. And so the labels are just these simple one-factor labels. We'll look at a more complicated example in just a minute. Okay, so now F, the color factor, is nothing but the following. It's 1/4 C, hold on. Let me go back. So it's C3 dagger. Can we dagger this? How do you dagger something? Is Jalon there? Jalon?
Yeah, what's up?
Jalon, if I handed you this and I said dagger this, I don't mean kill it.
Yeah.
But I mean, it would be cool if you could, but if I said to dagger that, what would you have to do?
Complex conjugate all its like components and then transpose it.
Yeah, well, complex conjugating the numbers 1 and 0 are pretty straightforward. So really, this is just transposing. Okay? Then we want to put in a factor of lambda alpha. And then we want to put in C1. Boom. Okay, you see, this is actually pretty straightforward, but we have to give you the values of the C vector and the C column vector so that you can actually plug something in. Okay, so carrying right along, we will then have the blue with lambda alpha and the blue. Okay? By the way, when I wrote down the factorization of M into the QED part and then the color part, you might or might not have realized that I initially had lambda alpha and lambda beta, but that propagator in between actually had a delta alpha beta, which is just a delta function. So that's why I set lambda alpha and lambda alpha to have the same index. Okay. So now all we would have to do to figure this out is write down the lambda matrices. Okay, now the lambda matrices, I'm just going to write down 1, and then you can look up the rest of them. But lambda 1, it's a generator of SU3, so it's a sparse collection of a couple of 1s. Okay, so what do I do? Alpha appears twice, so that means I sum over alpha. So I would start by putting in lambda 1 and lambda 1, and then multiplying this all out. And this is going to give me a number, and this is going to give me a number. And then I do lambda 2, multiply this out, all right? At the end of the day, you can kind of see this is just going to take the 1, 1 component of this, and this is just going to take the 2, 2 component of this. So this is actually going to be a sum over alpha of lambda alpha 1, 1, lambda alpha 2, 2. But at any rate, if you plug in the 8 lambdas into this expression, then this comes out to be minus 1/6. Okay? Now, Danny. You there, Danny? Daniel?
Yeah.
Danny, is this an attractive or repulsive interaction?
Repulsive?
It's repulsive because we got a negative color factor, okay? And interestingly, it doesn't matter what colorful assignment. You can pick any of the colorful octet combinations, and they will always give you a negative color factor, which implies that this is a repulsive interaction. So you cannot have a bound state of two quarks, or a quark and an antiquark, which are assigned a colorful octet color assignment. Okay? But now let's see what's so special about the color singlet. And this is where it gets ugly. So for the color singlet, I'm not even going to write these up there. Because it turns out if you're putting something in a color singlet, I can't say that this is anti-red and this is red. Because anti-red and red are not a color singlet. Okay, so let me remind you of what the color singlet state looks like. It's what I called state 9. But it was exactly what you would expect if I said, and I asked somebody last time and they gave me the right answer, I said, what would be invariant under SU3? And that's red, red bar plus blue, blue bar plus green, green bar. Okay? But that's what's weird because these two, this quark and this antiquark, have this color assignment. But you can't say this is red and this is anti-red because you've also got blue, blue bar and green, green bar. You can't say that this is red, blue, and green and this is red bar, blue bar, and green bar because that would imply something like red plus blue plus green times red bar plus blue bar plus green bar. But this would include cross terms. Okay, so it's not equal to this. It's just equal to this. Huh?
Entangled in some way?
Yeah. Yeah. Definitely. So, here we go. This is the way that we are going to understand this. So we have to write this in terms of the C's. That's either 1, 1, 0, 0, 0, 1, 0, 0, 0, 1 as rows and columns. And this is the way we're going to do that. First of all, if I encounter the combination C1 and C2 together, 1 and 2, oh wait, this is what I do. This quark and this antiquark are in this color singlet. So what that means is that this should be, 1, 0, 0, 1, 0, 0, plus 0, 1, 0, 0, 1, 0, plus 0, 0, 1, 0, 0, 1. That's it. Okay, red, red bar. I mean, the bar doesn't mean anything right now. So red, red bar, or red, 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 blue, blue, and green, green. Okay? If I encounter C3, C4, and I'll show you where I encounter them in just a moment, then I have to use the same thing. Why I wrote that down twice, I'm not 100% sure, but just give me a little bit of space. Okay, here we go. So the color factor. Let's first of all remind ourselves of what the color factor looks like, and it's the same color factor as what I had before. So this is 1/4 C of 3 dagger, lambda alpha, C of 1 times, and this, I'm just going to put parentheses around these spinner sandwiches, times C of 2 dagger lambda alpha C of 4. Okay? Now notice, there is C1, C2, except I dagger all the C2 parts. So that means this is the C2 contribution, it's the second term. So I just dagger those. So this is going to give me 1/4 C dagger 3 lambda alpha times 1 over root 3, 1, 0, 0, 1, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 0, 0, 1, lambda alpha C4. Does that make sense? Does it? You following me? Give me a thumbs up. Nice. Okay, I see real thumbs, I see yellow thumbs. Thumbs work. Thumbs of any variety work for me. Okay. Now, and it might not be obvious, but this is what we have to do. Here is C3 and here is C4. That means we have to write this entire expression first as 1 over root 3 with a 1, 0, 0 here and a 1, 0, 0 there. Then we have to add to that 1 over root 3 times 0, 1, 0 there and 0, 1, 0 there. And then we have to add a last factor of 1 over root 3 times 0, 0, 1 here and 0, 0, 1 there. Does that make sense? Okay. There's no simple matrix multiplication which realizes this for us. We have to actually think about what are these indices telling us to do, because we can't move factors around and put them right next to each other and bang away with matrix multiplication. But at any rate, if we do that, we're going to end up with an expression, and I won't even write the whole thing down, but I'll write down what it eventually becomes. We end up having to evaluate something like this. Plus a lot more terms. Okay? And what we discover is that this actually becomes 1/12 lambda alpha ij lambda alpha ji. All right? Who wants to volunteer and tell me what that is? Lambda ij, lambda ji. Lambdas are matrices, so what kind of matrix manipulation do you think that is? Ross?
It's the trace of their product.
Exactly. It's the trace of their product, because if I thought about lambda ij, lambda jk, that's multiplying the two matrices together if they share one common index. So this will give me some BIK. But then if I take the outer indices to be the same, then I'm doing BII, which is taking the trace of the product. So this is just taking the trace over all products of the 8 lambda matrices and adding them together. So we can write this as 1/12 trace of lambda alpha, where again, since alpha is repeated, we sum over it. And this comes out to be 4/3. Okay? So, Stephen, are you there?
Yes.
Stephen, is this attractive or repulsive?
Attractive because it's positive.
Exactly, it's a positive factor that goes in front of the normal QED result, which tells us it's attractive. So this isn't changing it. Okay? Now, there's not a lot of depth to me saying that, you know, a singlet is attractive and a colorful octet is repulsive. You know, I'm just giving you an idea of how to manipulate the color factors. And I hope you see it's pretty freaking complicated, okay? But that's the way it goes.
Can we ever get 0?
Say it again?
Can we ever get 0?
No. I mean, you could probably cook up some combination of. No, I don't think you can get 0. I don't think you can get 0 because I don't think SE3 will carry you into any 0 configuration. All right, so I'm going to very quickly try and throw the baryons at you. And we'll just, this is partly just to show you how much more complicated the baryons are. And then we'll take this to the point of conclusion. Okay, so for baryons, okay, the first and painful thing about baryons is that there are 3 quarks or 3 antiquarks. We'll just work with 3 quarks. And so we're dealing with more than 2 spin states. We're dealing with 3 spin states. And you know, you just saw how bad the 2 spin state singlet was. You can imagine how bad the 3 state singlet is. So so you might ask yourself, well, what if I threw in 3 quarks and I kind of did an overall analysis of this, and it turns out that while we can do that, it's kind of a little bit tricky because this is not a single interaction which we can easily adapt to the QED and just get an overall color factor outside. We only do that with 2 quarks at a time. And also, for reasons which we'll talk about in a few minutes, it's probably not the case that there's just a single interaction here. There's probably multiple interactions, and so some of them might be attractive and some of them might be repulsive, and it might be kind of a little weird to figure out which one dominates. We're going to figure that out, but we're not going to analyze this directly. We're going to start instead with a 2 quark interaction. So let's think about now 2 quarks interacting instead of a quark and an antiquark. Okay, so I'll have 1, 2, 4, 3, and if I bang out the m for this using QCD, I get minus gs squared over 4, 1 over q squared times the spinner sandwich times another spinner sandwich. And these are written in detail in my notes, but I don't need to write them up there. And then we're going to get the color sandwiches, C3 dagger, lambda alpha, C1, C4 dagger, lambda alpha, C2. Okay? This is the QED contribution, and Joseph, this is the QED contribution to the scattering of 2 quarks. Do you think that's a repulsive or an attractive interaction?
Doesn't that depend on color, or wait, just 2 quarks?
Well, no. So now we're going back to QED. We're pretending that these are 2 particles or 2 antiparticles. We'll just say they're 2 particles. So it's an electron and another electron, or an electron and a muon. Do those exhibit repulsive or attractive interactions?
Repulsive.
Repulsive, right, because they have the same sign. So this time, the natural thing here is that this is repulsive. So if the color factor is positive, then it's a repulsive interaction. And if it's negative, then it's attractive. Okay? So now it gets a little bit interesting because in this case, we can't actually break things up into the octet octet set of states and the singlet set of states. Rather, okay, so I'm going to write this down. For CC bar, we had the breakdown of 3 crossed with 3 bar color states into an 8 plus 1 decomposition. Now don't worry, if you don't remember cross and plus, it's not that important. I mean, obviously 3 times 3 is 9 and 8 plus 1 is 9, so something about this makes sense. Okay? But there's actually representation-specific interpretations for these combinations. But all I want to do is I want to show you that if instead of CC bar, we consider just combining 2 colors, not a color and an anticolor. And remember, a colored and anticolor, when you combine them, you can always tell the color from the anticolor because the anticolor always has a bar over it. But if I combine 2 colors, then it's possible for me to exchange them or, things like that. So it's a different combination. So if I'm combining 2 colors, I have 3 cross 3, and this actually breaks into a 3 plus 6, where this is a triplet, of course, and this is a sextet. Okay? Where the sextet, or the triplet, I'll start with, involves these combinations: 1 over root 2, RB minus BR, 1 over root 2, GR minus RG, and 1 over root 2, BG minus GB. And then the sextet contains the following: RR, BB, GG, 1 over root 2, RB plus BR, 1 over root 2, GR plus RG, and 1 over root 2, BG plus GB. Okay? Now, staring at these for a minute, can anybody point out what's special about this set of linear combinations and what's special about this set? Can you read them?
The top one is antisymmetric, and the bottom one is symmetric.
Exactly. So this set is antisymmetric under the exchange of any 2 colors. All right? Whereas this set is symmetric. Okay? All right. Now, here's the interesting result, and I'm not going to actually work through this, but if I take a triplet state, so if I take one of these linear combinations and assign the C's based on being in one of these and evaluate the color factor, I get minus 2/3. And if I instead take a sextet state, I get 1/3. So which of these is attractive and which of them is repulsive? Anthony, are you there, Anthony? Anthony, yeah, you're there. Anthony. Anthony.
Sorry,
There we go.
I was in the bathroom.
That's okay.
Just heard you as you were looking at the camera.
Which of these is repulsive and which is attractive?
What is that, F trip?
F trip.
I'm going to say F trip is repulsive. It's attractive.
Yeah, this is attractive. This is attractive and this is repulsive. Okay?
Yeah.
Now, that just gives us 2 quarks, but I just want you to first and foremost notice that between 2 quarks, depending on whether it's a triplet or a sextet application, that's going to determine whether the interaction is attractive or repulsive. Okay, but a baryon is made of 3 quarks. So we've actually got to work a little bit harder, and I'm not going to go through the details of this, I'm just going to write down the result. For baryons, we have 3 quarks, so now we have to take the product of 3 color space states. And in this case, we end up with a combination or a decomposition that looks like this. Okay? This is a totally symmetric decouplet. These are mixed symmetry octets. And this is the totally antisymmetric singlet. And this is the only one I'll write down. It's 1 over root 6 RGB minus RBG minus GRB plus BRG plus GBR minus BGR. Okay? Now, it might not surprise you, though, that the totally antisymmetric combination of 2 quarks is what gave me an attractive interaction. And it turns out that only if I use the totally antisymmetric singlet configuration of 3 quarks do I get an attractive interaction. One where the attractive interaction components prevail. Okay? So this is sort of motivation or something of an answer to the idea that when we have 3 quarks that form a baryon, they each have to have a color assignment, but the only color assignment that actually we find in nature is when they are given this totally antisymmetric SU3 singlet color assignment. Okay?
Hey,
all right.
Alex, are those supposed to be times's or pluses in the...
Oh, sorry, these are supposed to be pluses. Sorry, you're right.
Just making sure.
Yeah. Okay. So again, I'm not going to put you through many calculations like this in your homework or anything. I just want you to see how incredibly complex and how group theoretic quantum chromodynamics calculations end up being. But now let's actually get on to the answer to the question, which I said was going to be sort of vague at best. But so there are 2 observations that we have to fight against. So first of all, quarks come in colorless bound states. Okay, we just found that if we took a quark and an antiquark pair, if we took a pair of 3 quarks or 3 antiquarks. And gluons exist in colorful octets. Okay, remember the gluons, we talked about how 3 by 3 gives us 9 potential gluon states, except the one SU3 neutral one is not part of these generators of SU3. Okay? Now there are 2 experimental observations which are interesting, which should play into this. We never see free quarks, and we never see free gluons. Okay? And both of these can simultaneously be the result of a single suggested mechanism, and that is color confinement. That is, there is nothing which exists in nature alone which has net color, which is a non-singlet state. Okay? Obviously, if I have a single quark, that has to be in a colorful state. There's no way to take a single quark and make it colorless. We can take pairs of quarks and antiquarks, mesons, put them into a colorless singlet state. That should be okay, and it turns out that's what we see in nature all the time. Okay? Actually, that's not what we see in nature all the time. We see mesons very rarely for reasons which we'll get to in a minute. But we can also take 3 quarks and form a baryon, which is an overall colorless state. And those are quark states which we see all the frickin' time. Okay? And the short answer for that, or the short reason for that, is because protons and neutrons are both baryons made of 3 quarks. Mesons, since it's a quark and an antiquark, mesons always have the potential to decay. Anytime you have a particle and antiparticle state, they can decay. So mesons don't live very long, but baryons are made of 3 quarks. There's no reason for them to intrinsically decay, although they can after some period. So this is an explanation, the fact that quarks have to exist in colorless combinations, of why we don't see lone quarks and we only see them in meson and baryon combinations. And it's also a statement for why we never see gluons at all, because gluons can't even be put in colorless combinations. They have to exist in these colorful octet configurations. Now, this is a hypothesis. Okay, this isn't something that's ever been proven. And the reason for that, and this is something which we'll get to at the very end of the semester, is associated with the fact that when we renormalize, and I'm throwing this word up here as a teaser for what we're going to get to at the end of the semester, but renormalization tells us that in many situations, the strong coupling is actually larger than 1. And that means that if we're doing Feynman diagrams as an expansion in the coupling, you can't just take the first couple of Feynman diagrams and get the answer. The later diagrams are more important. So the Feynman approach just goes out the window when we get to the realm where GS is larger than 1. Now what that means is that to really prove this color confinement hypothesis, we're going to have to appeal to mechanisms other than just using the Feynman approach. And it can include several interesting things. I mean, there's a whole non-perturbative approach to quantum chromodynamics, which is called lattice QCD, where you're basically setting up a lattice, you're defining your fields as these discrete not discrete variables, but these localized variables, and then you're running a Monte Carlo simulation. And there's a whole field in high energy physics which does lattice gauge theory, and they are trying to prove this color confinement hypothesis, but they still haven't been able to do it. I mean, this is a Nobel Prize winner if anybody can actually do the damn thing. Okay? Turns out that if you throw supersymmetry into the mix, then it becomes a little bit more tractable of an issue. And what's the other thing you can throw into the mix? Oh yeah, dualities. So dualities are a means of doing calculations which can oftentimes take a situation where the coupling is strong and rewrite it in terms of a theory which should give you the same answer, but it's in terms of a theory where the coupling is weak. So these are just fields in which people are still doing research. The color confinement hypothesis has not been proven, and the research goes way beyond the application of just the simple Feynman rules, which is what we usually apply to particle physics calculations. Now what I want to do for the last few minutes of class is I just want to accept this color confinement, okay, and go to that other question, which is, this is one of the two questions that I posed at the beginning of class, which is, why do the strong interactions for widely separated things seem weaker than the electromagnetic interactions? Okay? So let's see what's going on, and this is going to require me to draw a really weird picture in just a minute. But this will segue us into something really interesting, or hopefully interesting. Okay, so first of all, well, I'll write it this way. Alpha is the way it's usually put, but I'll just put, yeah, I can put G's. So the strong interaction coupling is larger than the weak interaction coupling, which is larger than the electromagnetic coupling. Okay? That is the direct order of couplings in most instances, and that might seem a bit weird because, like I said, at large distances, electromagnetism governs everything. The weak interactions and the strong interactions, they really don't play much of a role. So let's see if we can understand why. So consider proton-proton scattering. Okay, now why would I consider proton-proton scattering instead of, say, electron-electron scattering? Somebody give me an answer.
Because protons contain quarks.
Yes, we want to compare the electromagnetic and the strong interaction between two objects. If I did an electron and electron, it doesn't feel the strong interaction directly. It just feels QED. Okay? So we want to compare the interaction between a proton and a proton, therefore we get the electromagnetic interaction because they're charged particles, but we also get the strong interaction. Okay, so here we go. If I write down the QCD version of this, I might write down a picture like this. Okay, so this is a baryonic configuration of a down and two up quarks, and that's the content of a proton. Clearly, this down quark and this up quark are just coming along for the ride, okay? And this gluon in exchange is just between this up quark and this up quark. Of course, you could tack it onto any other quark in here, but this is just an example, okay? And then if I draw the corresponding diagram from QED, well, first of all, I don't have to worry that these things are made of quarks for QED. All I care about is that it's a charged particle and it exchanges a photon. Okay? And so looking at this, we would expect that since the strong interaction coupling is larger, much larger than the electromagnetic coupling, that this diagram should dominate over this one. Makes sense, huh? Right? I mean, you know, you've got two vertices here, you've got two vertices here, so they're each quadratic in the coupling. If the coupling is larger for the strong interactions, then this is going to be a larger quantity. Okay? Everybody agree? Okay, there are two problems with that. That's a very naive argument, but there are two problems with it. One is that this is a van der Waals type interaction. Why do you say van der Waals? Well, remember, this proton must be overall colorless. All baryons have to be colorless. And this has to be overall colorless. They can exchange a gluon, you know, because secretly this is made out of things which have color, and you might have an interaction between two of the bits, but that's a lot van der Waals. You know, van der Waals is the interaction of two atoms which are electrically neutral, but you know, if you put the electrons if you put the atoms in an orientation so that their electrons are closer to each other, they might exhibit a little bit of repulsion. You couldn't see that if you just said this is neutral and this is neutral, therefore there's no interaction, but they're distributed charges. So if this is distributed colors, maybe this colorful up and this colorful up or get really close and they interact or something, okay? This is not van der Waals at all. Damn it, that's the fundamental electric charge, and that's the fundamental electric charge. I mean in the positive sense, okay? So that's one reason why this is probably weaker than this, but there's another reason. This is not allowed. Why isn't this allowed? Hi, Ross. Thanks for waving.
Should I answer or?
Well, I don't know. Has it got any other takers? Avery, you're nodding your head. You want to answer? Avery. No. You're going to answer. Remember, these two protons are far apart.
Yeah.
So the gluon that they exchange has to travel a good ways to get from one proton to the other. So that means it's largely a physical particle.
Yeah.
It means like you could put a scanner in here and detect it or some shit like that. Can you have a single gluon exist? A single physical gluon, can it exist?
No.
No, that's what we just proved earlier on. Well, that's what we implied was a result of the color confinement hypothesis. Okay? It turns out that this diagram is just wrong. Let me draw you the correct diagram. So I'm going to have, oh boy, this sucks. So I'm going to have a blue quark coming in, which happens to be the up quark. And then that blue quark is going to happily transform into a red quark, which is the up quark going out, through the exchange of a gluon, which is actually going to interact with an incoming red down quark and that is going to shoot a downward going quark. And then we're going to have an incoming green quark, which is the up quark from here. It's going to turn into an outgoing blue quark, which is the second up quark leaving, via the exchange of a gluon. And the vertex of this gluon is going to generate the green quark, the green down quark, and it's going to bring in another quark. And then this guy, Jesus, is going to go down as a green quark through the interaction with the incoming green up quark. And this is going to be the down quark. And then we're going to have the, oh my God, this gets me drunk every time.
I gotta say, this is pretty complicated.
I know. The red quark interacts with this quark, giving me, maybe I should not talk and just draw the damn thing. That might be the easier way to do it. There you go. Look at that picture for a minute. Holy shit. But I want you to notice, red transitions. Okay, so let me see. So this is going to be a quark. This is a gluon. So if I've got blue coming in and red going out, this could be a downward going blue anti-red, which means when it combines with this red quark, this thing is going to come out as blue. Okay? And then green comes in, blue goes out, so that means this thing must be green anti-blue. When it hits here, the green goes out, and so this must be anti-blue. Now let's see if that works out with the rest of it. Blue hits this guy, forms a green, so that means this must be blue anti-green. That comes down here, joins with this green. The green cancel, and I have blue coming out. Holy shit, it works! I'm not going to go through the rest of the vertices. Trust me, they all work out. Okay? And then also this down quark gives me this down quark. This up quark gives me this up quark. Okay? It's an incredibly complicated diagram, but here's some very, very, very important features of this diagram. First of all, this is a proton interacting with another proton, and it is not through the exchange of a gluon. What is being exchanged in this case?
Another quark.
Well, it's actually a pair of quarks. It's a quark and an antiquark, which is what type of particle?
A meson.
A meson, and it's a colorless meson. This is a particle that can live in nature physically. That's what we proved at the beginning of class. So unlike in the previous simplified picture where I tried to say they swapped a gluon and a gluon can't exist physically, this meson lives fine physically. So you can separate these a long way, and this meson is still going to happily interact between the two of them. Now when we compared the QED picture, that was QED with the coupling squared in the QED diagram. How many vertices are in this bad boy?
It looks like it could be more than 2.
It's 8. Which of these two contributions do you think is larger? Remember, this is a perturbative approach, so that means that the coupling is less than 1.
one on the left.
Yeah, the one on the left is a much, much, much larger contribution. Okay? Now, there is another reason why this diagram is way weaker than the electromagnetic interaction between the two protons, and this is something we'll cover next time. But in exchange of this meson, the meson here actually has a mass. And when the force between the two particles is mediated by a massive particle, then you have to put in a massive propagator, and that introduces a mass term in the denominator, which can overwhelmingly bring down the magnitude of m. Okay? So there's lots of reasons why this diagram is way weaker than the electromagnetic interaction between the two protons. Okay? Now, here's an interesting observation though. We can take this entire story and we can, instead of considering proton and neutron, or proton and proton, we can think about protons and neutrons. Okay? That just means you take one of these up quarks and turn it into a down quark. Okay, so we can do down here, in which case this is down, and we can make this guy be a down quark, and then this guy's a down quark. Okay? So if you do proton, or sorry, no, I just wanted to make one of them a down quark. So we'll let this one still be a proton. Okay? What's interesting is that if you make one of them a neutron and one of them a proton, then if you calculate the amplitude m for this process, it's pretty much exactly the same as the amplitude for the strong-strong. So for QCD, it doesn't matter if you're looking at a proton interacting with a proton or a proton interacting with a neutron, you get the same answer. What about for QED? What do you think the answer is for a QED interaction between a proton and a neutron? Anyone?
Not a damn thing.
Not a damn thing. The neutron is electrically neutral. Okay? So this, of course, is why the strong interactions are very important at the nuclear level, because they're the attractive force between the proton and the neutron. And that's why if you start stuffing a lot of protons together in the nucleus, their nuclear or their electromagnetic repulsion can often be overcome by the nuclear attraction unless you get too many protons together. But then you can throw neutrons in the story, and the neutrons just increase the level of attractivity, and they can stabilize the nucleus. All right, now I'm just going to say one quick thing and let you get the hell out of here, but this is the punchline of all this. I have now given you QCD. You people are pros, kind of, okay? Yes, yes. I want to take you for just a second back to a time period before they understood this. Before QCD. And before QCD, they were trying to understand why it was that you could not, and QCD, by the way, is not just the statement that things are made of quarks, it's the statement of an SU3 gauge symmetry and the gluons and all that. But they were trying to explain why things were made of quarks, but you couldn't pull the quarks apart. They didn't use the term color confinement because color is part of the QCD story, but they were just trying to figure out, like, why the fuck can't you pull two quarks apart? Okay? And this is what they proposed. First of all, if you take two electrically charged particles and you draw the field lines between them, then they often do shit like this. Where they spread out all over the place. Okay? And it turns out that you can take a field line analysis and realize that you're always able to take two electrically charged particles and separate them with a sufficient amount of force. Okay? However, what they thought of is, what if in whatever is the attractive interaction of quarks and quarks that keep you from being able to pull them apart, what if the explanation for that is that the field lines between them are confined to only begin and end on the quarks? They can't just go off to infinity. Okay? It turns out that these field lines also contain the energy between these two, the interaction energy. And if you pull these apart, those field lines are exhibiting a tension. And you should know this. If something has a tension, the further you pull it apart, the larger the force becomes. That's what's important about a tension. Okay? That does not happen here. Here, in fact, the force falls off as you pull them apart. Here, though, if you confine the fields to just beginning and ending on the particles, then you get this tension which grows as you try and separate them, which kind of says you can't separate them. Okay? Now, what they did was they said, okay, let's take two quarks and really separate the shit out of them so that this is just a really thin line of condensed field lines. And let's study the fluctuations. At a scale of around 10 to the minus 15 meters, because that's about the size of a meson, of a pair of quarks. Okay? And so they started studying the dynamics of these fluctuations to see if they could figure out, yeah, this is actually the reason why you can't pull quarks apart. And it turns out that their study was totally screwed up. Okay? They experienced so many weird things. They experienced tachyons, particles that move faster than the speed of light. They experienced spin 2 excitations. But the standard model has only got spin 1/2, spin 0, and spin 1. So it's like, where the hell is a spin 2 excitation coming from? So this didn't work. And eventually QCD came along and it said, no, it's not confinement of the field lines. It's actually these 3 colors and these 8 generators and all of this shit. But there were 2 guys who said, fuck that, let's keep studying this. Because there's a spin 2 excitation. A spin 2 excitation tells me this is gravity. And so what they discovered is if instead of thinking of this as 10 to the minus 15, if they took it down to 10 to the minus 35 meters, and instead of thinking of these as quarks, they just said, fuck the quarks, let's just study the fluctuations in that string. They discovered string theory. String theory was discovered in an earnest attempt to try and answer why you can't separate 2 quarks. And it started out as an analysis at 10 to the minus 15, the nuclear level. But it had all these problems. It had gravity. We're not trying to do gravity here, goddammit. It had tachyons. Tachyons move faster than the speed of light. They're terrible. Okay? But these 2 guys were like, wow, wait a minute. These fluctuating strings are amazing because they predict gravity. And they discovered you could get rid of the tachyons. And thus was born string theory. About the same year that I was born. That's it for today. Any questions? All right. I'm reading your comments now, but I'll see you all on Thursday. Please make it if you can. It'll be an interesting experience to say the very least. Good night.
Wait, Florite?
Yes?
How on earth do you look at something that
so small.
You don't look at it. What they were doing was they were basically, so this is a point particle, and a line of flux between them. They were instead taking this entire thing as replacing point particles.
Alright.
So, I mean, just moving it down to 10 to the minus 35 was basically putting this at a length, which is the fundamental length scale in all of physics. It's the Planck length. It's a length below which we know we can't probe.
Okay.
Other questions? Okay, all right. Good night, everybody.
Bye.
Bye.